So when you're graphing and you're asked to graph your 3 times 2 to the negative x plus 2, first of all, you would think of your graph, your parent graph, which is 2 to the x, and it's going to have always 0, 1, and this time if I plug in 1, I'd get 1, 2 with an asymptote at y equals 0. So there's our parent graph, there's our basic graph. And we're going to graph y equals 3 times 2 to the negative x plus 2. And have to think about how does this relate to transformations that we had before. So first of all, what I'm going to do is I'm going to take out my highlighter, and I'm going to highlight the 2 and the x. And I highlighted that because that's my parent graph. One of the things that makes exponential functions a little bit harder is that your parent graph has a number in it. Whereas all of our other parent graphs didn't really have numbers. Like x squared had a little 2, but because it was little, you were able to deal with big. Like this has a big number. And for whatever reason, that makes it harder. Okay? Because you're going to have to worry about order of operations. You don't know how many people who see this 3 and that 2 so close together and multiplied, and you see yourself being tempted to write 6. But order of operations say you have to do all that exponent stuff first before you can multiply. So you can't do the 3 times 2 and make it 6 right now. So by highlighting this, everything that's left is a transformation. And we're going to just quickly label them right now. What did numbers multiplied in front do? Does that seem like you remember that as a vertical stretch? Numbers where the x was. So our x is in the exponent. So anything that happens where the exponent was, that's now all of your horizontal stuff. So this negative is a horizontal reflection. And this 2 is in the exponent. That's going to be a horizontal translation. And in chapter 3, we wrote a special note that says, if you had a horizontal reflection with a horizontal translation, what did you have to remember to write it as? Or what did you have to remember to do? And have to write it in factored form. This is our very first example is testing to see if you remember that. We're going to have to rewrite this as 3 times 2, and up here you have to write this in factored form, which makes it an x minus 2. So you might be tempted to say 2 to the left because of the plus 2. It's actually going to be 2 to the right. And unlike DAVC, there's no shortcut for exponentials. We're going to do the same system that we did back in chapter 3, where you took important points that you knew on your original graph. And we're also going to look at what happens for asymptote. We did all of our stretches and compressions first, and then translations afterwards. So we have a stretch here. This is y by 3, and this is x. So I'm going to write above here, I have to multiply my x by negative 1. I have to multiply my y by 3. Then the only translation is that we have to go 2 to the right. So let's see where these points end up. This will be 0 and 3. This will be negative 1 and 6. And 2 to the right will be 2 and 3 and 1 and 6. Then our asymptote, since your asymptote starts at 0, do you see that multiplying it by anything will never make a difference? The only thing that's going to make the difference is if your asymptote gets moved up or down. And we're not moving up or down at all, so we still have an asymptote at y equals 0. We can now graph this, and I always suggest drawing your graph new and separate from the first one, because with asymptotes, if you try to draw them on the same one, it just gets too busy. So we have y equals 0. We're going to have the point 1, 6, and 2, 3. So these are going down, so we know that it's going to go down towards our asymptote and up in this direction. This is our new graph, using our transformations from chapter 3 and our original parent graph. Now, based on this, we can answer these questions. Is it increasing or decreasing? Our final graph is decreasing. Intercepts, I have none. Hope you can see that there's going to be, because of that asymptote, there's no x-intercepts. But your y-intercept, again, I don't see it on my graph, so then I'm going to go to algebra. How do I find a y-intercept? I plug in 0 for x. If you plug in 0 for x, do you see that you would get 2 squared, which is 4, times 3, you'd have 0, 12. The equation of the asymptote is y equals 0. Domain is everything, and the range is y is bigger than 0. Okay? So this is the idea for graphing. It's the same as chapter 3. The only thing that's new from chapter 3 is we have a new parent graph. All of our transformations are exactly the same. Okay? In this new parent graph, anything that is, I'm going to just take out where the exponent is, because that's where the x is in our parent graph, that's all of your horizontal stuff. Anything that is in front of your graph or after your graph, that would be vertical. Like I could have had a +1 here, then we would move it up 1. But I didn't have that +1, so there was no vertical translation up or down. I would like you to turn to there's a blank page on page 357, and we're going to add some graphs. The first graph that we're going to add is another regular one, so we're going to ask you to graph y equals -5 times 3 to the 2x plus 4 minus 7. First thing you'd have to recognize is what is your parent graph? What is the basic exponential that we have here? It's going to be something with an exponent of x. Can you see that the base is 3? So if I take out my highlighter and I highlight the 3 and the x, I know that all of the other numbers are going to be transformations. Again, even though that -5 and 3 are right close together and multiplied, we can't write -15 because of order of operations. So quickly, think about 3 to the x. 3 to the x looks like this. It's increasing. It's going to have 0, 1. It's going to have 1, 3. It's going to have an asymptote at y equals 0. So we need to see what happens to these points. 0, 1, 1, 3, and what's going to happen to our asymptote at y equals 0. We do our our stretches and compressions first, then our translations second. So when I go and I look at this graph, can you see that you would be multiplying your x values by a half? Because x's are liars. That too means you multiply x by a half. Always multiply by the reciprocal. And you're going to multiply your y values by a -5. The negative is a vertical reflection, the 5 is a vertical stretch. Translation-wise, that +4 means we're going to go 4 to the left. That -7 means you're going to go 7 down. So let's see where our new points end up. X by a half is 0 and 1/2. Y by -5 would be -5 and -15. 4 to the left would give me -4 and -3.5. And 7 down will give me -12 and -22. What's going to happen to my asymptote? Well, multiplying is not going to affect it at all, because it's at 0. The only thing that's going to affect it, because it's a y value, is if you move it up or down. Since we're moving down 7, our asymptote is now going to be at -7. So if I was graphing this one, 1, 2, 3, 4, 5, 6, 7. Oh my goodness. Y equals -7. Then I have the points I have -4, -12. Oh my goodness. What's that? 8, 9, 10, 11, 18, 19, 20, 21, 22. I probably should have just gone by 5s. Life would have been easier. So I have -4, -12. Label that point. And -3.5, -22. In between these 2 points, do you see that you are going this way towards your asymptote? And we would go this way in the end. So when you draw a graph of an exponential function, you need to show 2 points, just like you have 2 points on your original function. That's enough. And the asymptote. Then the shape will always be a curve going towards that asymptote, and the other side going off to either positive infinity or negative infinity. Does it make sense that this one's going down because we had a vertical reflection? Sometimes it's nice to go through all the unhighlighted stuff afterwards and see, do I see my negative reflection? Sometimes the stretches and compressions are harder to see, but they're there. Has it been moved down 7? Sure looks like it has. So that's the first graph that we're going to do. And now our second graph, I'm going to introduce you to a new number. Do you know the number E? It's even, I think it's on your formula sheet. They tell you on your formula sheet, I don't know how many digits that they give you on your formula sheet. Can you find the number E on your calculator? Can you get your calculator to tell you that E is 2.71828? And then we're going to graph e to the x. Which is a very, very famous graph in calculus. Because of the special properties of the number e, it gets used a ton in calculus. E to the x just looks like every other exponential graph. It has 0, 1, and you have 1, e, which is 2.7. And it slopes up and has an asymptote at 0, just like all the other ones. And what makes, sorry, I'll give you a little hint into calculus. What makes e to the x so special is that calculus is about drawing tangent lines. So if at this point I drew a line that touched only that point, imagine that's a straight line. That's the tangent line at that point. It happens to have a slope of 1. If I drew a tangent line at this point, it happens to have a slope of e. And if I would pick any point, like if I picked 2, e squared, and I drew a tangent line there, its slope would be e squared. E is the only number that has this crazy property that if you draw a tangent at a point on the graph, the slope of the tangent line is exactly the same as the y-coordinate, which has huge implications for calculus, which you'll see and work with next year if you take an AP calculus. But that's why the number e is a special number. In fact, pi and e are numbers called transcendental numbers. They are irrational numbers that go on forever, but they have special properties, like pi is related to a circle. E is related to exponential growth and calculus. They have proven that there are an infinite number of these transcendental numbers. Weird things in math, they've actually proven that there are more of them than there are rational numbers. Even though there's infinite of both, which is, mine might be blown just a little bit here. There's infinite real numbers. I mean, there's infinite rational numbers. There's infinite transcendental numbers. They found out that there's more transcendental numbers in infinity than there is in rational numbers. They found out these are part of irrational numbers, so technically speaking, there are more irrational numbers than there are rational numbers, even though there's infinite of both of them. But the way that they've shown it is if you would take a piece of string and randomly cut it somewhere, you will always randomly cut it at an irrational number, not a rational number. That's kind of weird. So, with that in mind, the crazy thing is we know about pi, we know about e. In our world, we've only discovered about 20 or so transcendental numbers. And most of them are just like, oh, let's just times e times pi and make a new one. It's not really that new. But it makes me wonder if, like, pi is so important, comes up in so many things, and it's this weird transcendental number. E comes up in so many things, and it's this weird transcendental number. As human race, what other, like, there is probably some other special numbers out there that connect to so many things that we haven't really found yet. What are those numbers, and what do they do? I don't know, maybe they'll discover one with AI. They'll be like, here's another cool number we never knew about. So you could graph y equals 3 e to the x minus 2 minus 1. How would you do that? You would set up the points on your e graph. The 3 is y by 3, the 2 is 2 right, the minus 1 is 1 down. That's kind of fun. Because if you took 1 comma e and multiplied the y values by 3, does it make sense that you would get 1 comma 3? Is that hard to say? 3. And then if you subtracted 1, you'd have 3 comma 3 minus 1. Now, when you go to graph this, you're going to have to, like, I'm pretty sure your 2, 2 would be no problem. Your asymptote at y equals -1 would be no problem. How do you estimate where 3e is? Well, if you think that e 2.7, if you multiplied it by 3, you see you get 8.1 minus 1. This is approximately 7.1. So when you're graphing it, you just have to approximate where it would be. And you could graph things with a base of e as well. Questions, for example, 2 are 10 and 13.